Okay, so we'll talk about search, right? Search is obviously to find a value in a given data set, right? So let's say you have a data set as 10, 50, 30, 70, 40, 20, right? And you need to find 20 here, right? So first one is the simple linear search. Linear search is you iterate through the list, and where you find it, you can find the given position that becomes your um, the position, right? So you go from left to right. You can, in sequence, you go from left to right or right to left. You can go from right to left as well. Okay. So for example, here, I need to find some. So I'll start with something called as index. Okay, I'll call it as idx equal to 0. And I'll have a variable which will tell me whether the number is found or not. So I'll call it as found equal to false. Okay, I'll set it as false. Now I will iterate through the list. Okay, so for, I can use for, okay, the list for I in, now I'm using idx and found, idx because, assuming that, the for loop is not giving you. So, you will increase the idx value one by one. So for I in range, or you can use while loop. Okay, while loop says, okay, let's do while loop. Okay, for loop becomes, let's do using for and while both. Okay, okay, so for I in range, okay, for I in range, now you can say len of, okay, len of L1. For I in range, len of L1. Okay, so that you're iterating from 0 to the length. Okay, and I'm going to compare if your if num equal to L1 of I, right? If this is the case, then you'll say found equal to true, and your IDX becomes I, right? That's the index, and then you break it. So once you're done with the for loop, you check if number is found or not. If found, then you say print, something like this. Num is in the list at IDX. Okay. Else you'll say number is not found. Num is not in the list. Okay. And when you run it, okay, so 20 is at position 5, right? 0, 1, 2, 3, 4, 5. Correct? Now, if I make it 200, for example, then it says is not in the list. Correct? And if you say 10, maybe, okay, it should say it is at the index line at 0, right? So this is called linear search, where you're going step by step. If you want to implement same thing, you can use while loop as well. So while x is less than the x is idx. So idx is, so what I'll do here, I'll take same stuff, num idx. Okay. Okay, so here I'll say while your idx is less than len of L1. So if len is 6, it should be up to 5, correct? So well, idx is less than this, and found, okay, equal to false, right? Is false, because the moment it becomes true, that means you are done and you don't have to go any further. So now you search for the value here. if num equal to L1 of IDX. Okay, if num is equal to L1 of IDX, then you say your this found equal to true. Else you can say IDX is IDX plus 1. Right, so you're moving the IDX, and again same thing. You found, right, and here you say you get this value here. So same way of doing it. So this is linear search, which is kind of easy. You go step by step, okay, and you can find out. Second type, and which is mostly used, is your binary search. Okay, so binary search works on sorted lists. So to work on binary search, first you have to sort it. And instead of going from left to right, okay, you go from the center. Okay, you check the value at the center. Okay, so if I have to take you through the paint, so you have okay, so you have, let's say this is your first and this is your last, right? So sort it, right? So you're looking for numbers. So first you go at the middle and check if this is equal to this. If it is equal, great. If it is not equal, then check whether this is on left side or right side. Okay. So if it is on right side, if that value is greater, right? So if let's say you're searching for 30 and this is 20, that means your value is on the right side because the list is sorted, right? So in a way, you're avoiding to check so many values at one go, isn't it?
Yeah.
Then you search here, okay, and let's say this is 25, let's say. Then again you are avoiding this, and then you are searching between these two. This is the most effective search. Okay. So how do we do that? Let's go back to our program and let's take same thing for now. Okay, and I'm going to say binary search, right? So for we need to find the mid value, correct? Okay, but before we do that, so list has to be sorted, correct? So you say L1 dot sort. Okay, and now if you print this list, okay, you can see that this is sorted 10, 20, 30, 40, right? So we use, okay, sort the list before use. Okay, now let's come back here. Okay, so what we have to say is this IDX, okay, which is what we're going to track. This should be, okay, you start with 0, right? And this IDX okay, how do we do that? Okay, so first we need to find the mid value.
So like center by what we did yesterday for sorting.
Right, the insertion sort, right? Yes. So here too, okay, we will find the mid value. Mid value is nothing but okay, so mid, you are looking at the index, not the value exactly, right? So it's going to be let's say IDX is is 0. Okay. And then so instead of saying IDX, okay, okay, this is what we are going to track, right? So I'm going to say low, comma, high. Okay. And this is going to be 0, comma, your len of L1. Correct? And now I'll put a loop. Okay. And the loop should run, okay, such that okay, so for now let me put while, okay, true, or instead of while true, your low has to be less than high, correct? The moment low becomes greater than or equal to, okay, we should stop, right? So low should be less than high and font should be false, right? Then you continue. The moment you find it, okay, that's the end of this. Now here your mid is low by high.
Yeah.
Low plus high divided by 2, right? Now I'm going to check if L1 of mid is equal to our number. If this is true, then your IDX is mid, right? And mid, and your found equal to true. Okay, so that's it. And else your, okay, now in else we have to change the mid to high or high to mid depending upon the value. Now if this, you can check here, so I can say instead of else, if I say elif, okay, elif L1 of mid is greater than num. Okay, so mid value is greater than num. That means num is on the left side. Correct? Num is on the left side because mid value is higher. So your num will be on the left side. So mid value is higher. So your left should remain at left. I mean, low should remain at where it is. High should come to the mid. So you will say here high equal to mid. Else, that means your number is on the right hand side. Number is greater than the mid. Then the low should come to the mid. And I think that is it. Okay. We'll go and copy the same stuff and see. And to test it, let's run it and see. Third value, I'll say something like binary search. Okay. So that we know the result is from binary search. Okay. Now when you run it, okay, 0 is in the list 0, right? We got it correct. Now to test it, okay, you have to test it for all kinds of values. Okay, we tested for first. Let's test for last one, 70. So what happens if we say num equal to 70? Okay, as 5. Now I can test something which is in between, 30. Okay, now you should test something which is not in the list, 300. So testing is also an art, right? So, okay, now binary, if found, why it's not getting printed? So found will remain false, isn't it? Wait. Okay. No, oh, this is still running.
Oh.
Ah, okay. See, this is still running. That means, okay, low it should be low less than equal to, let's see. No, still it's running. Why? So while has to break, right? Now found equal to true, and you can say break here. But okay, so this is anyway good, okay, but that, see, what is it? The meaning of it is that low is not becoming equal to high. Okay, low is always less than high. That's why the loop is going forever, right?
Yeah.
While low, because we're using and means even one condition is false, okay, it is false. Now break here is not required, because when we say found equal to true, this will break. This will become false. Entire thing will become false, and the loop will break. Only thing is when the value is not found, okay. Um, okay. So see here, what we'll do here. See, mid, we are anyway checking mid value, correct? So remember the example that we discussed in guessing the number game.
Yeah.
Okay, so let's say here, we'll modify it a little bit. So let's say you have number line here, right? And let's say you're checking for a number here. So this is your low and this is your high. Okay, so high is always less than low, and sorry, low is always less than high. That's why it ran into infinite loop. Now let's say if you're finding this value, and if this is mid value, and value is not equal to, correct? So if value
Yeah.
is not equal to, then there's no need of moving low to medium or high to medium. Okay, high we can move medium minus 1, and low we can move medium plus 1, right? Mid plus 1, because mid is anyways, that value is not there. So instead of moving low to mid, let's move low to mid plus 1. Okay, so let's go back to our program, and we'll say low high is mid minus 1. So you are moving to the left of mid, and low will become mid plus 1. You're moving right of mid. Now in this case, there is a chance that low will become greater than high, and this will break. So now you see 300 not in the list. Okay, but we have to check again the last and the first. And last and the first works, that means it's all good. So last is 70. Does it handle 70 well? Yes, it handles 70 well.
Yeah.
Does it handle 10 well? So you run it and see 10 well. Yes. Now you see, if we had not checked for negative values, so when you check, positive means something will give you the expected result. Negative means, okay, what if value is not in the list? Now, if we had not tested, we wouldn't have caught this error, right? We could catch this error because we tested for negative values also. If we were happy, okay, that, we got the value and, we move ahead, then it becomes little like, you think that your program is correct, and then, but it turns out to be that program is not completely correct, isn't it?
Yeah.
Okay. Make sense?
Yes.
Okay. So with the, these are the two search we use.
Oh, only two, okay.
Yes. All good? Okay.
Yes, sir.
Now we'll move to our binary tree, right? So what is binary tree?
Basically, nodes packed together using a
Right?
tree-like
Bin
system.
means 2, right?
Yeah.
Okay, so every node has we say at most. Okay, because if you have only two
Should I
numbers
do
to
something
handle,
on the whiteboard or?
no, not yet.
Okay.
So because see, when you have only two values, right, then obviously your binary tree is not complete, right? So that's why we say, at most, okay, at most two child node, okay. So then you have, let me know. Okay, go to whiteboard. I'll just put here binary tree. Okay, so binary tree, as I said, it will have, you have a node, and at most two, nodes, two child nodes. Okay. Okay, so this is your binary tree, right? At most means, let's say if you have three values, then this is the structure. If you have four values, then this will be the structure, right? So that's why, this, in this case, it has only one, right? Not two, right? So, so that's why we say at most. Then you have something called as full binary tree. Okay. So what does that mean? Okay. Full binary tree means each of your nodes should have exactly two or none, right? So this is not your full binary tree. But if I add this one here, now it is full binary tree. Now this is full binary tree. Okay. Full binary tree means each node should have exactly two or zero, right? This does not have. So this becomes what we call as leaf node, right? Which does not have is called leaf node. And this is called your full BT, binary tree. Okay. Then you have something called as perfect binary tree. What is perfect binary tree? Okay. Perfect binary tree, all the leaf nodes, full binary tree, okay, full binary tree, which has all the leaf node at the same level. Understood? Full binary tree, which has leaf node at the same level. So if you take this one example here, so you have one node, and this will have two. Now this is perfect binary tree with depth 1. Okay, then if you go to another depth, this is another binary tree. Correct? This is another binary tree. If you go to another depth, this is another perfect binary tree. When I say so, perfect binary tree. Yeah. So if n equal to 1, how many nodes do you have in perfect binary tree? 1. Node equal to 1, you have only 1. Okay. So you have 1. When it is 2, then how many you have? 2. When it is 3, then how many you have? When it is 4, how many you have? So it is like 2 power 0, 2 power 1, 2 power 2, 2 power 3. Okay, it goes on like the next will be 2 power 4, 2 power 5. Okay. So this is called as perfect binary tree. Okay. So full binary tree, perfect binary tree, and we also have something called as complete binary tree. Okay. So see, this is so perfect binary tree is a subset of full binary tree, correct? Special case of binary tree. And complete binary tree is also a like your full binary tree, okay, where the leaf node should be on the left. Okay, what does it mean? So if you take, this is a full binary tree, and see, this is, okay, you have this. Now each node should have 2 or 0, right? Now this is also example of full binary tree, FBT, full binary tree, because each node has either 2 or 0. Okay, but this is not perfect binary tree, or this is not complete binary tree. Complete binary tree, the leaf node should be on the left side. So if I put it something like this, here, and these 2 nodes goes here, it is complete binary tree. Complete binary tree. So you have full, perfect, and complete. Now let's say you have one more node. If you have one more node, then this should be here. Now this in, okay. So okay, so if I see, okay, if I see this way, this is your full binary tree as well as complete binary tree. This is only full binary tree. This is not complete binary tree. This is your complete and full, both correct, but not perfect. Why? Because this one does not have. Leaf node should be at same level, isn't it? Now, if I add a node here, this is still complete binary tree. What it says that if you have node should be first completed on left side.
Oh, it's complete binary tree even if there's no 2 nodes?
Correct.
Okay.
Because if you have only 6 values to play with, right, then, okay, this is what you'll do. So this is not perfect, this is not complete. But sorry, this is not full, this is not perfect, but this is complete.
Okay.
Now, if I add one more here, now this is an example of perfect, complete, and full, all 3. So in a way, perfect is both full and complete, but vice versa is not true. Okay. Now there's a special case called pathological tree. Okay. So pathological tree, every node will have only one child. Okay. That is called, pathological tree. Okay. Then comes your balanced binary tree. So you have full, which will have either 0 or 2 node. You have perfect, okay, where all the leaf node are in the same level. Then you have complete, where, okay, it's a perfect binary tree with values on the left side. Okay. Now you have balanced binary tree. Balanced binary tree means your left side node should have value. Okay. Okay. So, the difference, okay, what we say is, if you look at the root node or the parent node and the left node, the difference should be only 1 or 0. Okay, what does it mean? So
You're saying that if you put what's it?
I'll show you with an example. Okay, so let's say we have one node here. Okay, and you have another node here. Okay, so it is a binary tree in which the difference between the height of the left and the right subtree, okay, height of, okay, so this is 1 here, let's say, and this is 2 here,
Yeah.
and this is 3 here.
Okay.
So what is the difference of this height? 2 minus 1?
1.
1.
That's also 1.
Yeah. So that's why we say this is binary tree.
Isn't in the binary tree,
Balanced
isn't
binary
the
tree.
left side always smaller than the top one?
That is special case. We'll talk about it.
Oh, okay, okay, okay.
Okay. Okay. Now, when you talk about this, again, we talk about traversing, right? In order, post order, pre-order.
Okay.
Okay. So let's try to see that. Okay. We'll go and build the traverser. So we are back to our computer screen, and we'll create node first. Okay. So how do you create node? We'll say class node, right? Or you can say class BT node to differentiate between linked list and others. Like if you are doing same file, you can say class LL node, class BT node. Okay. So class node, and then we define the init function. So init, and here you need the key, right? The value that has to go there. And your self dot value is the key, correct? And then it should have maximum 2 nodes, right? So you'll say self dot left equal to none, self dot right equal to none. Now you perform what is called as pre-order traversal. Traversal. In your pre-order traversal, you define, okay, pre-traversal or something, traverse or something, let's call it. Okay. Now let's see how we do that. So in pre-order, what we do, we take left side. No, it's always respect to root, right? So root should be the first one to be printed.
Okay.
Correct?
Yeah.
So you always have the root to be printed first, then you move to the left side, and then you move to the right side. So first you print the node that you are at. So print, okay, self dot value, correct? And you want to print all the values, in the same line. So we'll put comma here. After printing the first, next one you have to print the, which one? Left. Right? So you will say if left exists, if self dot left exists, okay, then you have to say self dot left dot your pre-traversal. Okay, this is called as what function? Recursive function.
Recursive, okay, yeah.
Right? We call this recursive function. Right? We call this recursive function. And once you're done with left, now you have to do with right. Now you need to do with right. So we'll say right. If right exists, then do this. That's it. Now, how do we call this? So to call, we'll create a root node first. We'll say root equal to your node, node, right? And we'll pass value, let's say 1. So root node is 1. You want to add something to the left? You say root dot left. Root dot left equal to node 2. So I'm adding 2 on the left. root dot right equal to node. Let's say I add 3. So now the two levels are completed. Root completed, root dot left and root dot right completed. Now let's add one more to the root dot left. So I'm going to say root dot left equal to node 4. Now root dot left. See, you can give a name also, right? Okay, L1 equal to root dot left, and then you can say L1 dot. Okay, you don't have to say dot multiple times. You can give it a name and then you can do it. Instead, it does, we can give same thing here. So root dot left dot right equal to node of 5. You are able to visualize it, correct? Root dot right dot left equal to node 6. Let's add node 7 also so that we get it here. Root dot right equal to node 7. Perfect. Now you want to perform the traversal. Okay, we have built only one, and something similar we can build for others, right? So we'll simply say here, okay, root dot pre-traversal. So it starts with the root basically. Are we printing it here? We are printing it here. So when we run it, I think it should print. Now you see 1, 2, 4, 5, 3, 6, 7. Let's see this. Is it correct or not? So let's go to the paint. And we are saying 7, right? So we started with 1, then we said 2, then we said 3, then we said 4, 5, 6, 7. Okay, pre-traversal. Pre-traversal means 1 followed by left side, followed by right side. Correct? This is what it means. Correct? So 1 followed by left side, followed by right side. Now left side is 2 followed by its left side and followed by its right side. So luckily here you have only 2, right? So 2, then left and 5. This is what it means. And this side you will have 3 and then 6 and 7, right? So net will be 1, 2, 4, 5, 3, 6, 7. 1, 2, 4, 5, 3, 6, 7.
Okay.
1, 2, 4, 5, 3, 6, 7. Correct? You got same output. This is your pre-traversal. Then you have in-traversal. In-traversal means, okay, you need to print left side, then center, then right side. Correct? So I'll copy this whole stuff. Okay, and I will say here in traverse or something like that. In traverse, and you change it to in traverse. So in traverse, first you go to the left, then you print the center value. Correct? So now if I go and I say root dot in traverse. Oops, so I have to give because we give slash n, right? In traverse. Okay, so 4251637. We can go here. Let me share my entire screen for a second. Right? So in traverse, right? So in traverse means left side and right side. So first left side, followed by 1 and the right side. So here you have, yeah. So here you have 425.
Yeah.
425, then 1, and then 637.
Mm-hmm.
Right? This is how you got 425, 1, 637. So you can try, you can keep on building more and you can try.
Mm-hmm.
Same thing, you can build now right traverse. Right traverse means the first two if will be first
Yeah.
and then you have the
Yeah.
print. Right? So always left, then right.
Okay.
The center will change based on which you are doing. Okay, you are doing in or left, I mean pre or post. Okay, so this is how you perform binary tree. Give me a second, I'll just see what we have next. 1 second.